Northrop Grumman's Talon program reflects a larger transformation underway in how the United States prepares for future air conflicts, and understanding its significance requires looking at the aircraft, the design process, the strategic environment, and the broader shift in U.S. defense priorities. Talon is not simply another unmanned system, it is a demonstration of a new approach to building combat aircraft that are intended to complement and extend the capabilities of America's manned fighters while being produced at a pace and cost structure that supports sustained operations. The United States is facing a world where the volume of platforms, the speed of adaptation, and the ability to absorb losses without degrading combat power have become increasingly important. This means rethinking how aircraft are designed, manufactured, and fielded, and Talon embodies that rethinking. The development of Talon occurred over approximately 15 months, which is exceptionally rapid for a stealth-oriented aircraft. Traditional U.S. aerospace programs often require years of design maturation, wind tunnel studies, subsystem integration, and iterative testing before producing even a single functional prototype. For Talon, the design and build cycle was compressed through extensive use of digital engineering tools that allow engineers to validate structural concepts, aerodynamic shaping, systems integration, and maintenance considerations without requiring the same volume of physical prototypes. The team also balanced these digital methods with hands-on experience from Scaled Composites, a company with a long history of quickly producing functional prototypes by simplifying structures, minimizing part counts, and using composite materials efficiently. This approach reduced Talon's total part count by roughly half compared to Northrop's earlier prototype for the Air Force's first CCA increment. Reducing part count is a major advantage because each part represents cost, machining time, supply chain risk, inspection, and net assembly workload. A lower part count directly affects the speed with which a program can scale from prototypes to production. Weight reductions of approximately 1,000 pounds were also achieved through design simplification and full composite construction. In combat aircraft, reducing weight can improve range, endurance, and maneuverability, while also simplifying the load on landing gear and structural supports. When considered alongside the emphasis on affordability and mass production, the weight reduction helps maintain competitive performance without resorting to costlier high-performance subsystems. Northrop Grumman made it clear that Talon was intended to maintain much of the capability envelope of earlier designs but at a far more sustainable cost. This required trade-offs. Instead of pursuing the absolute maximum performance in every subsystem, they sought a balance that keeps Talon capable while making it feasible to produce large numbers if required. The shaping of Talon suggests an aircraft designed to operate near advanced threats. While its exact radar cross-section remains undisclosed, its configuration shows a deliberate effort to minimize signature while maintaining aerodynamic efficiency. The lambda wing shape provides a balance between internal volume for systems and structural strength, while also enabling control authority without large surfaces that would compromise signature. The V-tail arrangement is consistent with low observable aircraft, as it reduces side and rear reflectivity and helps manage infrared signatures by shielding parts of the exhaust plume. The dorsal air intake serves two major functions. It reduces the aircraft's forward radar signature by hiding the compressor face of the engine and frees up the lower fuselage for potential internal payload volume. Autonomous combat aircraft require space for sensor packages, communication systems, mission computers, electronic support measures, and potentially weapons. The area beneath Talon's centerline includes a large geometric panel with sawtooth edges often associated with low signature doors, strongly indicating that the aircraft is designed to deploy payloads internally rather than externally, which would otherwise compromise low observability. The autonomy of Talon is one of its most strategically relevant features. The United States is moving toward a model where human pilots control teams of unmanned systems that expand the reach of sensors and weapons far beyond what a single aircraft can provide. Talon is not intended to be remotely piloted in the traditional sense but instead operates under mission-level autonomy. This means a human gives the aircraft objectives, and the onboard systems handle routing, formation keeping, sensor usage, and threat response within defined parameters. The autonomy software, known as PRISM, has already been tested on a different platform, reducing integration risk for Talon. In operation, this autonomy allows Talon to act as an extension of U.S. fighter aircraft, increasing their situational awareness by deploying forward sensors, offering additional weapons capacity when needed, or performing high-risk tasks such as pushing into the densest threat areas. Human pilots can thus remain at safer standoff distances while still influencing the battlespace. This reflects the American doctrine of preserving highly trained aircrew in expensive manned aircraft while employing unmanned systems as force multipliers. The strategic environment in which Talon is being developed makes the program particularly relevant. The United States is preparing for potential conflicts where advanced air defenses, large-scale drone use, and extended supply chains will influence outcomes. High-value aircraft are irreplaceable in terms of skill and cost, but they cannot be everywhere, and they cannot be risked in every situation. Talon contributes to a strategy where layered airpower distributes risk across a wider set of platforms. Instead of relying solely on a small number of high-end fighters to perform every mission, from intelligence gathering to suppression of enemy defenses, the United States can field a mix of manned and unmanned systems. Talon and similar autonomous aircraft can move ahead of manned aircraft to identify threats, test enemy radar behavior, create openings in defensive networks, or carry weapons that increase overall strike density. A major part of Talon's significance is tied to industrial capacity. The United States has identified the need to modernize its defense manufacturing base to handle higher production rates. The idea is that a future conflict could require rapid replacement of lost unmanned aircraft without the years-long delays seen in older procurement cycles. Northrop Grumman's leadership stated that the primary goal behind Talon was not only to deliver an aircraft but to demonstrate a process that can be applied to many future aircraft. This means modular engineering disciplines, digital design integration, supply chain simplification, and streamlined assembly lines. If this process works at scale, it can enable the United States to sustain air dominance in situations where competing nations rely on mass production of lower-cost systems. Talon also reinforces U.S. partnerships. By developing a platform that is adaptable, affordable, and operationally relevant, the program positions itself as an appealing option for allied militaries that seek to modernize their air forces without incurring the costs of fifth-generation fighters. The United States benefits from having allies equipped with compatible systems that integrate into American command and control networks. Such alignment enhances collective deterrence by extending the reach of shared surveillance, strike, and defensive capabilities. Talon's modular mission architecture allows it to be tailored to the operational needs of different partners while preserving interoperability with U.S. systems. Talon demonstrates how the United States is preparing for a new era of airpower, one characterized by speed of development, modular autonomy, scalable production, and cooperative operation between manned and unmanned aircraft. It supports a vision where air dominance is preserved not by relying on a few highly advanced aircraft alone, but by fielding a layered, resilient force capable of adapting to fast-changing operational environments. The United States is positioning itself to remain ahead of adversaries through a combination of technological innovation, manufacturing agility, and integration of autonomous systems into its broader combat architecture.